stability of a control system is defined as bounded input is given to the system, then bounded output is obtained. It is a common definition that BIBO is when input is bounded, output must be bounded. If input given to the system is 0, output also must be 0 irrespective of initial conditions. This is the common definition for stability. Now, there is another definition that was given in the earlier classes also, that impulse response of a system must be 0 in the steady state. Any time response, it consists of two states, transient state and steady state. So, when impulse input is given to the system, its impulse response must die in the transient itself. So, another definition that impulse response as time tending to infinity, that is in the steady state, must be 0, then we say that the system is stable. Now, stability can be defined based on operating conditions. Stability can also be defined based on operating conditions. For example, if you take a closed loop system, generally it is represented by K and zeros in the numerator and poles in the denominator. Whereas this K is a steady state gain or DC gain. Based on operating conditions means the system is stable for all the values of K. For example, K lies between 0 and infinity, then we say that system is stable, but it is absolutely stable. For all the values of K gain, if the system is stable, we say it is a stable system, absolutely stable system. Conditionally stable. Next, conditionally stable, for example, if the K lies between 10 and say 120, then we say that it is a conditionally stable system or limitedly stable system, because the range of K is limited. So, limitedly stable system or conditionally stable system. And if at all, if impulse response is not decaying to 0, if it has sustained oscillations, then system is said to be marginally stable. This is another way of defining based on the operating conditions. We say that the given system is marginally stable if its impulse response has sustained oscillations. Now, stability can be even defined in terms of pole location in the S plane, that is complex plane. Stability can also be defined based on location of the poles in S plane. If for the system to be stable, all the poles must lie in the left half of the S plane, then we say that the system is stable. And second, if any repeated roots or repeated poles lie on j omega axis, then system is unstable. This situation when you have repeated poles. Repeated poles on j omega axis, we say that system is unstable. If one or more poles lie in the right half, in right half of the S plane, system is again unstable. You can see that if all the poles lying in the left half, no problem, system is stable, and if any repeated poles on j omega axis are even at origin, if there are repeated poles, we say that system is unstable. And even one or more poles lying in the right half, also the system is said to be unstable. And if you just see in this topic, what actually we are going to see is there is a stability criteria defined by Routh, Hurwitz developed a stability criteria in algebraic approach. They have invented that according to this RH stability criteria, we need to form a RH table, Routh's array it is called, and for that we need to have a characteristic equation. The denominator of the transfer function, the denominator of a transfer function is known as characteristic polynomial. If you see this 1 plus g of s into h of s, it is known as characteristic polynomial, and this is the input for RH stability criteria. And let us see today what is this RH stability criteria, and we try to solve some problems using RH stability criteria to indicate that whether the system is stable or unstable or marginally stable. So, before actually proceeding to RH stability criteria, let us have an idea of, for a given function, what is its impulse response, what is the location of the poles, and based on the location of the poles, can we assess the status of stability. For example, it may be a system, a simple system, then what is its impulse response, then the stability assessment. For example, if you take the system as 1 by s, there is one pole at origin. So, the location of the pole is at origin, and if you see the impulse response of this is 1. Laplace inverse of impulse response is 1, and the graph for this with respect to time, this is the output or response. So, we say that this is just stable or strictly stable, or it is marginally stable when the pole is at origin. Now, let us take the function as 1 by s square, means there are two poles at origin. There are two poles at origin, that means repeated poles, repeated roots on origin indicates what? That indicates the response is t, Laplace inverse of this 1 by s square is t, and this is the response. So, we say that this is unstable system. This is unstable system if you have repeated poles on origin. Let us go further, 1 by s square plus 1. This inverse of this, that is impulse response, is sin t and t, and you have sustained oscillations whose frequency is 1 radian per second, and the location of the poles for this is on j omega axis. So, 1 by s square plus 1 indicates two poles on j omega axis, because s square plus 1. So, s square is equal to minus 1, s is equal to plus or minus j 1. So, this indicates there are two poles on j omega axis whose impulse response is sustained oscillations, and we say that the system here is marginally stable. Marginally stable. So, let us consider the function 1 by s square plus 1 whose impulse response is sin t, that indicates this impulse response sin t as a function of t will be having sustained oscillations, and the pole's location in the S plane plus or minus j1 for this system, indicating that two poles on j omega axis sustained oscillations means the stability, we say that it is marginally stable. That means beyond this system goes to the instability region. If you have the function like 1 by s square plus 1 whole square whose impulse response is t sin t. Here also you have an oscillations, but that oscillations of increased magnitude. That means t sin t versus t, if you see, this is the way you have an oscillations. So indicating that there are repeated roots on j omega axis. There are repeated roots on j omega axis. So it is an unstable system because that impulse response is increasing in magnitude. So it is not decaying oscillations but increasing oscillations. So the system is unstable if you have such a system because there are repeated poles on j omega axis. If you have only one and one pole on j omega axis, it is still stable, but beyond that system goes to the unstable region. Now if you have a function like this 3 by s plus 2 whole square plus 3 square, then the Laplace inverse, that means impulse response for this function is e power minus 2t sin 3t, where this 3 indicates the frequency of oscillations, that is radians per second, 3 radians per second. But you have this exponential term decaying. So if you see the response as a function of time, this function, you have oscillations, no doubt, but they are exponentially decaying oscillations. It is a good indication that the pole's location in the S plane is -2 j3 minus j3. So this is the location of poles. So they are in the left half, but of course complex conjugate pair, and indicating that system is stable because its impulse response is decaying. So we say it is a stable system. If you go further, instead of plus 2 whole square here, if you have 3 by s minus 2 whole square plus 3 square, exponential function becomes now e power plus 2t sin 3t. So it is reverse of this, that the frequency of oscillations same, but the magnitude goes beyond, because the two poles of complex conjugate pair, but their location is in the right half. Their location is in the right half of the S plane plus 2 j3 minus j3. So this is the location of poles in the right half. So we say that system is unstable, and also impulse response is exponentially increasing. So it is an unstable system. This is unstable system. Let us see one more function. System is described by 4 by s minus 2. Then its impulse response is 4 e power 2t. So if you see the response as a function of time, it starts and exponentially increasing. So as you know that it is very clear from the given system, the pole is located in the right half of the S-plane at +2. So this is an unstable system. So location of the pole or impulse response are the indicative of whether the system is stable or unstable. Let us move. The given system is represented by C of S by R of S. This way, non-unity feedback control system, and this is given by K S plus Z1 S plus Z2 so on, S plus P1 S plus P2 and so on. As you know that numerator terms are zeros and denominator terms are poles. Now for stability, according to this Routs and Hurwitz, this is known as characteristic polynomial. So 1 plus g of s into h of s equal to 0 is known as characteristic equation. So the roots of this characteristic equation are known as poles of the given transfer function, and for stability such roots must lie in the left half of the S-plane. That is a general criteria according to the transfer function definition. For stability such roots must lie in the left half of the S-plane. Let us consider this characteristic equation as a0 s power 4 plus a1 s power 3 plus a2 s power 2 plus a3 s plus a4. Say this is a characteristic equation, and for this equation, if I want to find the stability, it is important to know there is a necessary condition. Necessary condition is all coefficients of this equation must have same sign. All coefficients must have same sign, and no term should be missing. No term should be missing. That means all the terms must exist. If it is a fourth order system, so you should have all s power 3, s power 2, s power 1 and s power 0. So there should not be any term missing, and all coefficients must have same sign is the necessary condition for the system to be stable. Now necessary and sufficient condition. Necessary and sufficient condition is according to RH stability, criteria, we need to form a Routs table. This is called RH table, is to be formed for the given characteristic equation, and the first column of the Routs table should not be having any sign changes. There should not be any sign changes in the first column of the Routs table for the system to be stable. So if no sign changes, if there are no sign changes in the first column of RH table, then we say that system is stable. And if there are some sign changes, so number of sign changes for the coefficients of the RH table, number of sign changes in the first column indicates that many roots lying in the right half of the S-plane. That many roots lying in the right half of the S-plane, so the system is unstable. So that information we get from Routh-Hurwitz stability criteria, that is how many poles are in the left half, how many poles are in the right half, and if there are any poles on the j omega axis, etc. Not only that, we can also know the conditional stability. If you take K as a system gain, so what is the range of K for the system to be stable, we can find out from RH stability criteria. If the system has undamped oscillations, we can also find out the frequency of oscillations from RH stability criteria. It is a very important algebraic criteria. Using that, stability can be assessed, and let us see how exactly we determine the status of stability when characteristic equation is given using this stability criteria. So let us consider the characteristic equation of fourth order. By seeing the equation itself, you can assess the necessary condition for stability, that all the terms are available. There is no term missing and all the coefficients have same sign. So we can say that necessary condition is met, so system is stable. The necessary and sufficient condition for stability must be known from RH stability criteria, and characteristic equation is required for that. And for this, you need to create an RH table. So what is that table? You can see here the highest order of S is 4 here. So you can just indicate S power 4, then S power 3, and then the coefficients of S power 4 is A0, S power 2 A2, and the constant A4. The alternate terms, coefficients, must be written in the first row. This first row is based on the highest power of the characteristic equation. Next, S power 3, the coefficients of S power 3 is A1, then alternate terms A3, and nothing here 0. So first two rows of RH table are from the given characteristic equation. Now you create an S power 2 row, S power 1, and up to S power 0. Any equation given, whatever may be the order, you must have to go up to S power 0. Now how to get S power 2 row elements? This is simple. Actually, A1 A2 minus A3 A0 by A1. The first element of S power 2 row we need to calculate from the given data. This data is from the characteristic equation coefficients. So call this as B1. Now the second element of S power 2 row is product of these two, A1 A4 minus, this is 0 anyway, so by again A1. So for entire row of S power 2, the denominator is the first element of the previous row. Now this is B1 and this is A1 A4 by A1, so this is actually A4 only. Call this as anyway B2. Now the S power 1 row is B1 A3 minus B2 A1 by B1. this is the way you should obtain B1 into 0 minus B2 into A1 by A1 again. So, this is the way you should get S power 1 rho, and S power 0 is product of these two, and then nothing is there here, you can assume 0. So, it is again this product divided by this component, you will get B2 directly here. So, the first column of Routh's array, we need to focus only on the first column of the Routh's array. There should not be any sign changes in the first column. So, remember, no sign changes in the first column of RH table, then we say that the system is stable. If there are any sign changes, so number of sign changes in the first column indicates that many roots lying in the right half of the S plane. So, let us consider one problem based on this RH stability criteria, and let us see what are the methods to assess the stability of the system.